go through the answers to these revision questions then, so on half-life. So if we have a look, the table shows how the count rate from a radioactive substance changes in 10 days. The count rate starts at 880 and then you've got some points to plot there. So it says draw a graph of count rate against time. The first 2 points have been plotted for you. So this would actually be worth 3 marks. 2 of the marks are for plotting correctly. So the first point is 880, then you've got 555, and then you've got 350 at 4 days. So 4 days, 350 is there. Okay, you can use a ruler to help you if you need to. 6 days is at 220, which is there. 8 days is at 140. And then 10 days is at 90. And then the last mark is for joining a line of best fit. Now it's not a straight line, it's a curve. So the best way to do that is to turn your paper around, use your wrist as a pivot, and then you draw a smooth line up. Then the next question says, use your graph to find out how long it takes the count rate to fall from 880 to 440. So you'll need a calculator for that. Hang on, I've left mine over the other side of the room. Let me just go get it. Okay, so it starts at 880 and you need to go to 440. So 440 is here. So with your ruler, draw a line across to your line of best fit and then down. And for me, that is 3.2 days. And then the question says, what is the half-life of this substance? But this is a trick question because what you've just calculated is the half-life. Because you went from 880 to 440, 440 is half of 880. So that is the half-life. So it's 3.2 days. Right, next. The table gives some half-life and type of radiation given out by different radioactive sources. Some samples of each isotope have the same count rate today. Which sample would have the lowest count rate 1 month from today? The one with the lowest count rate will be the one that decays the quickest. Because that means that on its graph, its count rate would decrease much quicker than another one. So on the same day you can see this one has a lower count rate than this one. This one's at 200 and something, this one's at 500 and something. So the one with the shortest half-life will have the lowest count rate. So the one with the shortest half-life is radon 222. Okay, the reason it has the shortest half-life. Okay. Number 2. Student measures the level of radiation from a radioactive source during the same lesson each week over a period of 6 weeks. Here are the results they've collected. So you've got your weeks here and the radiation, so that's counts per minute here. Using the graph paper below, draw the results in a most appropriate way. It's worth 5 marks. This is just for plotting a graph. So at the start it's at 66, which is here, times 0. So times 0 for the start. 1 is at 44. 2 weeks is at 34. 3 weeks is at 29. 4 weeks is at 16. 5 weeks is at 12. And 6 weeks is at 8. And then we need to draw a line of best fit. But if you look, there's like a dodgy result here. You need to draw a smooth curve. So I would ignore that result. It looks like an anomalous result. Turn your graph paper around, use your wrist as a pivot, and as you can see, you get a nice smooth curve through as many points as possible. And what overall pattern is there in the students' results? Basically, for the 3 marks, if you work out the half-life, you get the 3 marks. So what we need to do for the half-life is we go from 66, so 66 divided by 2 is 33. So what we need to do is draw a line across to your line of best fit at 33 and then down here. And on my graph that looks like 2.3. The half-life is about 2.3 weeks. Yeah, ish. It might be different on yours, it depends where your line of best fit is. And that gets you all 3 marks. You could say that the radiation decreases with time. As well. Okay. Right, last one. This one's a bit harder. Questions go from easier to harder. So this one, some rocks contain the radioactive isotope uranium-235. Uranium-235 has a half-life of 700 million years. And it decays, as it decays, lead is formed. So it makes P7.5. So this is the original nuclei, and this is what you make. Draw a decay curve shown on the graph, but it's a bit of a strange one because here at the side it says proportion of uranium remaining. So at time 0, you've got to do it by ratios. At time 0, the amount of uranium would be 1 and the amount of lead would be 0 because you haven't made any. Okay. After a 1 half-life, this would have halved, so this would be 0.5. And because this is now 0.5, this is 0.5 because they both add up to 1. So 700 million years, 600, 700, I've got to go to 0.5, which is there. Okay. After another half-life, this will have halved again, 0.25, and because they've both got to add up to 1, that'll be 0.75. So 0.25 after another 700 million years is 1,400 million years. So that's here. And we are at 0.25, which is here. Yep. Okay. So you can do one more if you want. If you halve this again, so after 3 half-lives, this will be half of this, so it'll be 0.125. Okay, so 1,400 plus 700 is 2,100, which is here, and we've got to go to 0.125, which is about there. Okay. And then we've got to draw the decay curve. So again, turn your page, use your wrist as a pivot, and you make a nice smooth decay curve. And it says use the decay curve you've drawn to estimate the age of the igneous rock. Okay. So it says here samples of igneous rock gave a ratio of 70 atoms of uranium to 30 atoms of lead. So we need to make this ratio look like these ratios. So if we divide by 10, we get 7 to 3, and if we divide by 10 again, we get 0.7 to 0.3. So that's the one we're looking for. We're looking for when uranium is 0.7. So go to your graph, draw a line across at 0.7. and then down here, and you get about 400 million years-ish. Okay, you're allowed plus or minus 100. Okay, that's a really, really hard question. I mean, it's one of the hardest radioactivity questions, but that's good because at least if you can go through it and sort of understand it, then you will be able to answer the hardest question. Just the last point, you don't really need to know this, but we'll just quickly go through the answers, not in your specification. A sandstone rock which lies above igneous rock contains traces of uranium-235 and of lead-207. Why might it be unsatisfactory to use this uranium for dating the sandstone? It's because because sandstone is sedimentary, there was probably already lead 207 in the rock when it was made. So it would be then unfair to use it in a ratio like this one because it was probably already there, because sedimentary rock's made from other types of rock. What you want to do is use it from igneous, because that's when the rock comes out of the is cooled down from lava or magma, so then it would be fresh, if you like. Whereas this rock, sedimentary rock, that could have been around before anyway. Okay, hope that was helpful.